As usual, I would like to request everyone to keep yourself muted, but do feel free to unmute yourself and ask questions during the talk. So I'm very excited to introduce Professor Luis Ntaimo from Texas A&M University, where he's currently the Sugar and Mike Barnes Department Head Chair of the William Mike Barnes 64 Department of Industrial and Systems Engineering. Professor Ntaimo obtained his PhD in Systems and Industrial Engineering in 2004 from the University of Arizona, and his primary research interest is in deriving models and solution methods for decision-making problems involving uncertainty and risk, system modeling and process optimization, and computer simulation. Recent applications of his research includes patient and resource management in healthcare, wildfire management, air traffic flow management, aircraft assembly line production optimization, and energy reduction in data centers. His research has over the years been funded by NSF, Department of Homeland Security, and as well as various sources from the industry. Professor Ntaimo is a member of the Informs and ISyE, and he is the past president of the Informs Minority Issues Forum. He currently serves as the associate editor for Informs Journal of Computing, IISc Transactions, IISc Transactions on Healthcare Systems Engineering, and SN Operations Research Forum. As well as he's on the editorial board of the Journal of Global Optimization and Computational Optimization and Applications Journal. So today he will talk to us about expected conditional risk measures for risk-averse multi-stage stochastic programs. Professor Ntaimo, thank you very much for accepting our invitation. And whenever you're ready, you can start.
Thank you, Krishna. I really appreciate the kind invitation. And it's been a pleasure meeting with faculty since morning. We've had very productive conversations. So I'm very excited. I wish I could be there in person, but you know, it's a virtual world that we have entered in with respect to COVID-19. So the next few minutes, I'll share some ideas about the work that I've been doing with three colleagues of mine on risk-averse multi-stage stochastic programs. We basically derived a new risk measure, which we call expected conditional risk measure for multi-stage stochastic programs. We understand risk measures well in the two-stage setting, but we wanted to investigate, you know, in the multi-stage setting, you know, can we come up with something that we can easily use using standard decomposition methods for multi-stage stochastic programs. And we applied it to two applications, hydrothermal scheduling and portfolio optimization. In today's talk, for the sake of time, I will talk about hydrothermal scheduling. So this is joint work with Mariam Katami. She's a former student of ours here. Now she's at Indiana University. And then Tuena is in Brazil. The application I'm going to talk about is a Brazilian power network. Tuena is the guy who actually implemented the methodology we developed, and also the results I'm going to show just briefly. Those results are just a sample of what we have, which was done by Tuena. And my colleague, Bernardo Pagnoncelli, you know, he's the one who actually motivated this idea of expected conditional risk measures. So I appreciate my collaborators. And with that, I'll give a motivation of, you know, why we did this. And then instead of going straight into multi-stage, for the sake of the graduate students, I will start with two-stage, okay? So once I define the two-stage, I'll take my time and also define a few risk measures. Then I can briefly talk about multi-stage and then quickly, you know, give an application example for you to see, which is the hydrothermal scheduling. And then I'll summarize the talk. Now, before I get into the motivation, since I'm a department head, I just wanted to let you know about my department. You know, we we are a big department nationwide. So last year we got named the William Michael Barnes Department. We got an endowment of over $10 million. So we have a new vision for our department. We want to be in the top 5 in the next 5 years. We want to continue to be, you know, a place of excellence in terms of research and education. We have 4 main research areas: advanced manufacturing, data science, human and health systems engineering, which is human factors and ergonomics. And of course, historically, we've always been focused on operations research as a department. And I fall in this area, operations research. We have very nice facilities here. Our faculty numbers are large. We have about 50 faculty members, 30 tenure track faculty, lots of undergraduate students. This semester we have about 900 total, 900. It's a huge, huge department. The graduate population total is about 260. Our numbers have gone down by about 15% from last year due to COVID-19. So our graduate program has been affected adversely. Right now, we are recruiting in the area of data science, data engineering. For those of you who are finishing up your PhDs, you can apply. We are also starting a new degree next year, an undergraduate degree in data engineering. So it's a very exciting time, I think, for IE in general. So with that, now I can start talking about, you know, stochastic programming. You know, if you're not familiar with stochastic programming, it's an exciting field dealing with optimization problems involving you know, decision-making under uncertainty. So essentially, we have problems where we have to decide now, but we don't know the future. So how do we make good decisions accounting for the future? So the problems involve data uncertainties, which can come in different forms. Today, I'm going to talk about one specific type of approach, which is the recourse approach. You know, since the world is uncertain, I think it's imperative that when we make decisions, we somehow account at least for the uncertainty. In fact, Ben Franklin said, in the world, nothing is certain, okay, except death and taxes. So there are many applications of stochastic programming, which actually has motivated me to work in this area for so many years. You know, I've worked in healthcare, forestry, manufacturing applications. Today I'm going to talk about power generation planning, hydrothermal scheduling, which is done in Brazil. But also we have done some work in portfolio optimization. My collaborator, Bernardo Pagnoncelli, is in the business school in Chile. And so they do a lot of finance. That also motivated some of what I'm going to be talking about today. So when we make decisions in stochastic programming, sometimes we like to think of decision trees where we have a, you know, the timeline goes this way from left to right. And then at some point we have to make a decision, but we may not know the future. We may not know the outcome or the scenario that may happen, but we have to decide. And then, you know, one of these scenarios happens. And then after that, we again have to repeat the process. You know, we have to make another decision and, you know, the process continues. So a random event is a point at which information becomes known. Now, when we make decisions here and now, typically we don't know what the future is going to be. For example, you know, if we are planning for hydrothermal scheduling, they have to make decisions on which power plants they have to operate. They have hydro, which is clean, and they also have thermal power plants, which are not very clean for the environment, but they have to plan ahead, like 5 years in advance, which ones they're going to commit. And then they have to make projections about the future, which is, you know, the amount of water each year that they're going to get from the rainfall. So they talk about the reservoir levels every month for the next 5 years. But then they have to commit now. So that's the challenge. The other aspect to this problem is risk. So risk is the probability of loss. So there is a lot of need to include risk aversion in optimization problems. And this has been recognized in the literature because using risk neutral decisions sometimes is not a good thing to do, especially when you have extreme outcomes, extreme scenarios. And so here we are interested in being able to protect and guard against extreme scenarios. So we want to make decisions so that, you know, when bad things happen, our decisions are going to, you know, make us be in a good position. That's the idea. Whereas risk neutral, if things are good, you know, we can make good decisions if we just follow the risk neutral approach. So in the two-stage setting, risk aversion, I think is well understood and widely applied now. In the last few years, we have seen a lot of work in multi-stage setting as well. And so in the multi-stage setting, again, I can use a scenario tree to illustrate this. We have to make a decision here, X1, time period 1 or stage 1. We don't know what's going to happen. One of these scenarios happens, then we're going to end up there and have to make that decision. And then from there, we look at the future. Again, you know, here, two things can happen. We go here, two things can happen. Now, if we look at the overall scenario tree, we can see that there are different paths that we can take, but we don't know which one we can take. So we want to make our here and now decision before we see any realization of this. And this is what makes this problem challenging, especially when we have to consider risk, because we want to account for what may happen in the future. If we have a bad event, are we going to guard against that? And so in the next few slides, I'm going to introduce this notion of risk. But before I do that, let me just briefly, you know, talk about what some other people have done. In the multi-stage setting, the classical approach is what we call the nested approach, where we have to enumerate every node of the scenario tree that I just showed. And that becomes extremely challenging to do, especially when you are trying to define what risk is, because you're going to basically compound for every node the decision you make and the measure that you use. For all those time periods, you put that together and then you define your risk. Another approach is to use what are known as end of horizon risk measures, where we compute risk, you know, from the beginning all the way to the end. So we're trying to compute risk for the entire horizon. And there have been several works that have been done. Another approach, which is what we take, is to look at multi-period risk measures. So we want to basically look at, if I'm at time period 1 or stage 1, I want to be able to compute the risk for that time period. And then I go to the next time period and the next time period and so on. So when we do multi-stage problems, a lot of things happen when you are, you know, if you're risk neutral, it's okay. The problems are hard, but if you have to compute risk, then you have to carefully do it, because you want to make sure that the decisions that you make are going to remain optimal, regardless of what outcome you're going to have in the future. And so this motivated us to consider this expected conditional risk measure, where, as you will see soon, we basically condition based on the stage, based on the time period, in order to maintain good properties. And one of those properties, which I'm going to explain, is the time consistency, to make sure that the decisions that we make, regardless of the outcomes that are going to happen in the future, will remain optimal. So ECRMs can be defined for different risk measures. In this work, we focused on mean risk measures from stochastic programming, two-stage setting. And so, I'm just gonna mention these. I'll define them for you mathematically. I'll show you the slides, but I'll focus on one of them, which is the expected excess. Basically, we compute the deviation above a given target. The expected deviation above a given target is the expected excess. And then we have another risk measure called absolute semi-deviation, where the target is the mean, the average. So you want to minimize the deviation from the average, the expected deviation. And quantile deviation is a two-sided risk measure where you minimize the expectation above and below a quantile. Another risk measure is, which is very popular, and most of you should be familiar with CVAR. It's the conditional value at risk, which minimizes, the expected worst outcomes above a given alpha quantile. So basically, you're gonna define and specify an alpha level you want, and then from there, anything above that is bad in the minimization sense. We consider cost. So you don't want that. So you want to minimize the expectation of those waste outcomes. So these are classical risk measures that have been used, and we're going to apply them in this ECRM. Now, this is our contribution, but also in order to solve these problems, once we do the formulation, we need a way to do it. And so we have to apply dynamic programming or Bellman equations. So we have to derive these Bellman equations so that the problem is nice, and then we can apply it using standard frameworks. And for multi-stage stochastic programming, the two frameworks we use are nested decomposition or stochastic duodynamic programming. Or approximate dynamic programming. So in our work, we basically used SDDP. And then applied it to, two applications. In this work, we're going to focus on the long-term hydrothermal scheduling problem. Okay, so these are our contributions for this particular work. So now I'm ready to begin the math. So I'll start with just a very basic classical two-stage stochastic programming. If there is any questions, Krishna, just just interrupt me, and then I'll be able to answer questions.
Sure.
I just want to make sure we kind of lay the foundation quickly and then get into the mathematical details. So, stage one, in two stages, we want to make a decision X. It's a vector. We want to make that decision here and now. And I'm usually going to define X belonging to capital X, which is going to be a nice polyhedral set. The first stage can involve integer decisions, that's okay. And then we observe the future. There is a realization. And then now in the second stage, we have to make a recourse action based on the decision that we made in the first stage. And so the classical stochastic program allows you to make a decision Y, which depends on the outcome omega, okay? So I'll use omega tilde to the two-stage case as a random variable, and omega is going to be its realization. And so when I look at the second stage, I also have a set of constraints that I have to, abide by. So these are the constraints I have to make sure I stay within this. But what we want to do is we want to find an X such that no matter what happens, no matter what the outcome is, this X is going to be the optimal decision, the here and now decision. Now, optimal, we're going to define a measure. So for the risk neutral case, we use the average, okay? The average, we minimize the average cost. So we write the problem like this. We are minimizing here and now cost, C transpose X, it's a linear cost based on the decision X, plus a future cost, which is the expected cost. That's why it's risk neutral. And we satisfy the first stage constraints. And then for a given realization of our random variable omega tilde, we have an omega, and we're going to have some support. Later on, we assume we have finite support. Then we basically minimize our recourse, we call this the recourse function. And the recourse function involves an optimization problem, second stage problem. This is where we are making corrective actions. In this work, we assume, these are continuous decision variables, which allows this Q function to be nice, to be convex, okay? In other works, we have integer decision variables, and this becomes non-convex, okay? Here we are talking about nice second stage. And so in stochastic programming, A is known as the first stage matrix, T is the technology matrix, it defines the technology involved in the problem, and W is the recourse matrix. Again, we make some assumptions that the problem is well defined, it's rational and so on. And then when we define a scenario, an outcome, we mean the realization of the data. So I define an outcome as omega. Actually, it's a vector. I have to map this to the actual data. So the data in the technology matrix, that's random, and also the right-hand side. The right-hand side could be demand, for example. This technology matrix could define, in our hydrothermal scheduling problem, it defines the technology involving, the power plants. How much water are we receiving? That's kind of going to be defined in this technology matrix. Okay. In the next few slides, I'm going to use F as my recourse function, which is going to also include the first stage cost. This is convenient for me to, when I start defining risk, it's going to be defined relative to this function, which is going to be my cost. Given an outcome omega, what's going to be my cost? Now I have a random variable here, so this cost is also a random variable. And so I have to compute risk relative to this random variable, because every decision I make X is going to give me, for a given outcome, I'm going to compute the cost. So that's why, when we talk about risk in stochastic programming, we are talking risk defined on the space of this function. Okay, so I'll define that shortly. So in the two-stage case, things are very nice. In the multi-stage setting, we're going to define multiple stages. So instead of having just two stages, we're also going to have a third stage, a fourth stage, and so on. So we make a decision in the first stage, we feed it to the second stage, then we feed that to the third stage, and so on. So we're going to basically create some type of dynamic programming recursive formulation. Okay, and some few assumptions that are very typical of stochastic programming. We're going to define, we're going to assume that this random variable is discrete with finite support. So we can have a problem we can solve. Theoretically, it can be, you can have continuous distributions and then discretize it. And so for each discrete outcome, we're going to have a probability of occurrence P of omega. The first stage is non-empty. We just want to make sure we can make a decision. And the second stage, in this case, we can assume it's bounded and so on, so that we can make sure we can make recourse decisions. So this is just to make the problem mathematically sound. Now, if you make these assumptions, you can rewrite the two-stage problem explicitly, assuming you have all the outcomes, you collect all the outcomes. And so now this becomes your expectation. So it's risk neutral. This is a large-scale problem, and it's a classical problem which has a nice structure, which we call the L-shaped structure. And we can apply Bender's decomposition. This function, the expected recourse function, is convex. And so we can apply, different decomposition approaches to solve this problem. However, the problem is hard because you can have, a lot of scenarios which can make the problem intractable. And we talk about sampling methods and so on. So this is the classical two-stage stochastic programming formulation. Now I can introduce the notion of risk. So instead of solving a risk neutral problem, what we are going to do is we are going to rewrite the expected recourse function with the first stage cost. We're going to put it together. Remember I said I'll use F. So I can write the expectation like this. So now I want to minimize the expectation plus the some type of risk measure. So rho is going to be my risk measure. So I'm going to perform, like the expectation computes the average. This rho is going to perform whatever risk measure we define. Remember, we have 4 risk measures that we can apply, at least for this setting. And we also include a weight parameter lambda. If lambda is equal to 0, this thing vanishes. We are back to the risk neutral case. So by changing the values of lambda, we can basically vary how risk averse we are. So, the decision maker can set this parameter, or this parameter can be part of the optimization. And then we can trace the efficient frontier. So we have the first stage now where we have to minimize the expectation plus the weighted risk. And then in the second stage, for a decision X, realization omega, we make our recourse action, okay? So now I can also include these additional, the definitions just to make sure this is complete, especially for the students who want to, see the slides afterwards. That this function is the same one I defined before. For a given omega, we want to compute the cost now plus the recourse cost, the second stage cost. But now we're going to define these functions on a probability space. And E is going to be our expected value, and rho is going to be the risk measure. Again, rho is going to basically map from this family of functions to the real line, and we have different risk measures that we can use. So the decision maker or the modeler, they can choose what risk measure they want. I should mention that each risk measure you use is going to give you, it can give you different decisions, okay? Because of the way we define these. So if you think expected excess is appropriate for your application, then you use expected excess. Absolute semi-deviation, quantile deviation, SIVA, and so on. So again, in terms of practicality of this, you also have to have an idea which risk measure may be appropriate for what you're doing. For the sake of the talk, I'll just focus on expected excess. It's much easier to kind of illustrate what's going on. Again, the scenario, when we say scenario, we are talking about the realization of these data in the problem, the right-hand side and also the technology matrix. All right, so now I've defined my 2-stage risk-neutral problem, and then I've extended it to the risk-averse setting. And now I can spend a few minutes, talking about the risk measures, okay? Before I get to the multi-stage, okay? That's where I'm headed. I want to get to the ECRMs, okay? So risk measures can be categorized into several groups, but for this talk, let's put them into 2 groups. One group is what we call deviation risk measures. A deviation risk measure is calculated based on deviating from a target. Expected excess, which I'm going to explain in more detail, actually computes the expectation of deviating from a specified target. So the decision maker is going to say, hey, here's my cost target. I don't want to exceed this cost. If I exceed it, then it's bad for me. So now when scenarios happen and you make a decision X, you don't know what the cost is going to be. If the cost exceeds that target, then you don't want that. So we want to penalize that. So in other words, we want to make decisions that are going to minimize the cost associated with exceeding that target. If we are below the target, then that's good. We don't worry about it, okay? And we define absolute semi-deviation in a similar manner, but the target is the mean, the average. And there's another one called excess probability. I'll skip this one. Quantile deviation risk measures are based on deviation from a quantile, okay? These ones, again, it depends on the application. Quantile deviation is going to minimize expectation on both sides of the quantile. You provide an alpha quantile you want. And then depending on the distribution, when you do the optimization, you're going to be minimizing the costs above and below the quantile. Remember, you make a decision X, and then you plug it in the function F, and then you compute that cost. And that's where we are defining these quantiles. And the SIVA, which I mentioned, the area which looks at the expectation of the worst, scenarios, the worst case scenarios. There has been work by Asna and others who defined coherent risk measures. And so for those of you who are interested, I just put this here for you, that these risk measures, we have checked whether they satisfy these axioms which allow for defining, a good risk measure, especially in finance. This is very critical. They talk about translation invariance, positive homogeneity, monotonicity, convexity. I'm not going to go through the details, but for us, we are interested most in convexity. We want to make sure that our risk measures remain convex, so we can use convex optimization methods to solve. But if you are interested in specific applications, you need to check these axioms to make sure you know what your risk measure satisfies. But I'll show you a table for our risk measures, which conditions they satisfy and which ones they don't. So let me now give a mathematical explanation for the expected excess risk measure. So given an X, so we're going to be making this decision X, and we define a target. So we're going to set a target. It's going to be a cost target in our case, since we're doing minimization. And we define a lambda, which is a weight on our risk measure. Expected excess is defined as the expectation of the deviation above eta. This plus operator here means that if you give me a random variable z, it's going to take a particular value, and I take the difference. If it is positive, the max, then I take it. If it's not, if it's negative, it means I'm below eta, I'm below my target. Then I just use 0. Okay, so here this risk measure picks up costs for outcomes that exceed the target. This is nice because many decision makers like to, they know about their process and they know the targets they want. They like the cost or the profit if you're maximizing, you're doing maximization. And so that's why I like expected excess a lot, okay? It's a very nice risk measure, and it's widely used as well. So in our mean risk optimization, what we do is we want to minimize, we do minimization. We want to find an X, an optimal X, that's going to minimize not only the deviation above the target, but also at the same time, we want to minimize the average cost. So mean risk stochastic programming involves these two things. You minimize the expected cost plus your risk. In this case, we are looking at risk in terms of the expected cost above a target, and we put that weight. If that weight is 0, it means that we are risk neutral. So this is nice because when we look at the decisions, we're basically going to have an efficient frontier. For a given lambda, what is the optimal X I should make for given outcomes? So that's what it means. So in the multi-stage setting, when we solve these problems, we actually get policies. So we are looking for an optimal policy. Yeah, it's a little bit more involved. But anyway, we'll get to that in a few slides. The next thing we need to do after we define this problem is to now, remember I gave you the two-stage formulation. We need to basically expand this function, combine it with expectation, and come up with a nice formulation we can work with. So again, this has already been done for us. And so for expected excess, it looks like this. It's very easy to see. So you have the expected value. This is the average. When you combine these two, what happens is that you can actually linearize this function here by introducing this is a V omega or nu omega. It's a V, looks like a V to me. Now this V omega, I want it to be non-negative because it's a deviation I want. I want to compute that positive deviation, so it's non-negative. And that positive deviation should be greater than or equal to if I take, this is my cost. So if I have an omega outcome, this is my first stage cost, plus my second stage cost, I put it over here. I'm computing the difference. And I want to minimize the expectation of that difference. Okay, so this is a nice way to rewrite the whole thing and linearize it. And now this we can solve. This is a large scale linear program or mixed integer program. Okay, if you have integrality on X. So we can solve this. We can apply decomposition methods on this. And so that's what we do with the two-stage setting. Now I'm gonna fly through the next 3 slides or so because I just wanted to show you these. So when you get the slides, you can read through these. We do the same thing for absolute semi-deviation. We replace that eta target with the mean, the average. But you know, the average is not easy. You have to compute the average. So you make a decision X, based on the outcomes, you compute the average. So every decision you make X is going to give you an average. And that's what makes these problems, this problem, especially this risk measure, very difficult to work with. Because computing the average is not a trivial thing. Whereas in expected excess, you know, you give me a target, it's just one number, okay, one cost or one profit target you want. So that's absolute semi-deviation. Again, we can do some math and can derive the deterministic equivalent problem formulation like this. Let me just say that this one is much more difficult to solve because you have a complicating constraint which links all scenarios. The reason is to compute a mean, you need to have all the outcomes, get the cost for each outcome, and then you can get the average. But of course, you know, there are ways to decompose this problem and do something about it. The next risk measure is quantile deviation. Quantile deviation is based on a quantile. So the problem can be written like this mathematically. You are computing the expectation of, for a given outcome, you're going to get the cost, but then you need a target. Now your target is going to be based on a quantile. So you're going to basically compute a var. So this is like the var. So the cost above and the cost below. So it's a two-sided risk measure. And then we can write the mean risk stochastic program like this. We can do some math and then rewrite it this way. And this is what we can, you know, work with in terms of optimization. And finally, SIVA. Okay, this is the one that most researchers have worked with. Again, SIVA, you're going to provide an alpha quantile that you want. Above that, you know, we say things are, you know, scenarios are bad. So you want to basically minimize the expectation of the worst outcome. So above that eta, now this eta is going to be based on your alpha. So you want things that, you know, the worst outcomes, you don't want those. This looks like expected excess, this part, but now your target is based on a quantile. So it's like a var. You can also write the problem this way, minimize the mean and then the risk. Another way to write this is to consider a convex combination of the two. Again, this has nice properties. And then you can rewrite the whole problem like this. Okay, so we have done work with all these different risk measures. I just wanted to kind of introduce them here because we use these now in the multistage setting. I think I promised you to show you this table that if you're interested in coherent properties, you can actually derive these. For each of the risk measures, we are interested in convexity. We satisfy convexity, which is great. And then if you do the mean risk, we also show that we satisfy convexity. So we can use these risk measures in our approach where we use the SDDP. All right, are there any quick questions, Krishna, before I get into the ECRMs now?
I don't see any question on the chat, so maybe
All
you
right,
can
all
continue.
right.
Yep.
Silence means consent, so
I mean, I do have some questions, but maybe I'll keep it at the end.
Okay, sounds good. So let's go through this quickly. So let me define our ECRM. It's a multi-period risk measure. Before I explain this, let me start with this. I should have put this before this, but the mathematicians can read this and see what's happening. So now I'm going to drop the omega tilde. I'll just use omega to make the notation simpler in the multi-stage setting. So omega is going to be my random variable. So if I have a random variable zt for time period t or stage t, okay? Now remember, zt is going to represent like my function f. It's a cost, it's a random variable. So that's the zt here. Then for my risk measure, rho, I'm going to introduce a t now. So it's going to be a multi-period risk measure. So for every time period, I'm going to impose that risk measure. Okay, so that's going to be rho t. But because I'm in the multi-stage setting, if I'm in time period t, I need to know the history of how I got there. Okay, remember the scenario tree? So I'm going to be tracing that, those nodes. And so I'm going to define a history. So I'm going to use t with brackets to denote, so if I have omega t with brackets, it means I'm looking at, starting from time period 1, then I look at time period 2, 3, 4, and so on, up to t minus 1. So when I look at a risk measure like this, rho of t, I'm looking at the history up to that time period, but I can trace where I've come from. This is going to allow me to carefully define my risk measure. The ECRM takes all these costs, random costs from time period 1 to t, where we compute the cost in time period 1. There's no risk because we know, right now we know the future. We know what's happening now. So we don't have risk, okay? In time period 2, because it's the next time period, something can happen. So there's risk there. So we impose rho 2. We apply the risk measure rho 2. Again, here the history is trivial because we just came from the first node, the initial node. Okay. When we go to time period 3, here we now need to look at the history, omega t2. So we need to go from the history, the previous time period 2, and then that takes us to time period 1. But in our risk measure, we want to compute the expectation. For time period 3, we're going to condition on the history up to that point. Then we do the same thing for the next time period until we get to the end of the horizon. So the expected conditional risk measure, ECRMs, is a multi-period risk measure which applies risk at every time period. And in doing this, we use conditioning. So we're going to condition at every time period, looking at the history. If we do the conditioning, this allows us to maintain time consistency, which means that the plan made today will not be changed in the future if the problem is resolved again, given a realization of the random variables. Now, if you don't condition, this is not necessarily true, as some of you who are in stochastic programming know very well. but I just wanted to kind of, labor a little bit on this, just for your information that, okay, this is a nice risk measure, ECRM, because it maintains time consistency. So what does it mean when we talk about conditioning? This is what we are doing. So whenever we have, let's say, a scenario tree like this, where we have time period 1, 2, and 3, stage 1, 2, 3, I have, at every node, in this case, I have 2 realizations. Then when we apply our risk measure, we condition. So in every stage, we go there, we compute, we apply the risk, but we condition on this time period. We compute the expectation for this time period. Then we cascade this back to this, and then we compute that, and then we get back to the initial node. In the nested decomposition, we go to every node. So we get to the leaf nodes, and then for this, we apply the risk. We bring it here. We apply the risk. We bring it here. And then we apply the risk here. We bring it there. So it's very different. So this is what ECRMs do, okay? Again, it's conditioning on every time period. So let me kind of hurry up a little bit here. So now let me define, remember I introduced the Z to make it convenient to define the risk measure, but actually we're gonna have cost functions. For the sake of simplicity, we have linear cost functions like we did before, where we introduce a T for the cost at time T, and the decision X we make at time T will depend on the outcome at time T. So now our cost function is gonna look like this. And so we can rewrite the problem like this. I mean, the minimization problem. We want to find an optimal decision from time 1 up to time T, capital T. In the first stage, this is the cost now, so we know now. In the second stage, we have to apply our risk measure. In the third stage, we apply our risk measure, conditioning on where we are, the history, and then we compute the expectation for that. We do that for the next time period until we get to the last time period. Now, the last time period, that's the end of the future, so there's no risk beyond that. So we basically look at the time just before the last time period, which is capital T minus 1, given the decision we want to make at the end, which is xt, we compute that risk. And then notice we condition. We always condition. And then we also have constraints at every time period, which we have to satisfy. So mathematically, this is how the problem looks like. But again, to solve these problems, we have to rewrite them in a nice way. So we have to apply, dynamic programming and derive Bellman equations. So I just wanted to show you how the Bellman equations look like for expected excess. We're gonna use recursion. So we are minimizing, so we are interested in the decision at the first stage, the beginning, here now. This is our cost now, plus the future cost. So we're gonna apply that expectation, okay? Now, because we are using expected excess, then this cost here, QT, which is the second stage cost, involves also computing the third, the fourth, and so on. So it's recursively defined like this. So if I'm at time t from 2 up to t minus 1, then I'm looking at the cost now plus the future cost. Now this cost is going to include risk. And of course, I have to compute my risk now, okay? Remember, we can linearize this. So we introduce a UT, it's a non-negative variable, which computes that deviation. Remember, we have to compute the deviation above the target, and it looks like this. Very nice. And then for the last time period, we define the terminal conditions, which is now there is no future anymore. So the problem is very nice. There is no expectation. There's no risk in the objective function. So using this, we can apply stochastic duodynamic programming to solve our problem. Okay. So we implemented the ECRMs in the SDDP setting. Tuena, our collaborator, is very conversant with Julia these guys, Dawson and others, they have actually implemented these packages where you can solve these problems, large scale problems. It's very, very nice. So they use Groby and Cplex in their implementation. And Tuena conducted several experiments for our two applications. Now, with stochastic dual dynamic programming, I don't have time to explain it, but it's a classical algorithm where we do sampling, we do a forward pass. So if you have a scenario tree like this, you can select a number of samples you want to use in the forward pass. In this case, you can take the blue ones. And then when you get to the terminal, the end, then now you do your approximation, you do a backward pass, and you trace back through all these nodes. And then you continue the process. So the algorithm iterates several times until, you know, the upper bound, lower bound gets very small. Then you can stop and get your optimal policy. So that's kind of the idea. But again, this is another topic to explore. But let me quickly just give you some information, some insights about the application in the next few minutes I have here. The long-term hydrothermal scheduling problem deals with the planning and operation of power generation, where the uncertainty is represented in the inflows. So they have hydro power plants. The amount of water in the reservoir depends on the precipitation. So that's the randomness there. But they want to decide whether they should use power plants. Of course, they want to use hydro power plants all the time if they can, satisfy the demand, the load. But often it's not sufficient to just use hydro. So then they are forced to use, thermal power plants. This is Brazil. Other countries use nuclear as well, which has, cost because of pollution and other things. And so in this particular problem, we were trying to plan for power generation by coming up with what power plants should be used in every month for the next 5 to like 7 years, okay? So the optimization problem looks like this. So again, I define the several notation for you who are interested in looking at this, but I can just define it here. So we are trying to minimize the cost of using generation from thermal power plants. So P is the power from a thermal power plant. There's a cost. Hydro is considered free, so we don't have to worry about hydro. But we also have to make sure we satisfy the load. If we don't satisfy the load, then we have load shedding. So there's a huge penalty for load shedding, plus the expected future cost. This one is risk neutral, but we apply risk-averse to this particular setting. And then we make sure we have the balance equations. This is the load. The demand is known in this case. But we want to make sure that we generate enough power from thermal power plants, plus the load shedding, and then the power we generate from hydro, QT. Okay, plus there's a parameter here to convert it to power. And then we also have the reservoir constraints. In the reservoir, we need to look at the reservoir level we had in the previous month, plus the inflows. The inflows are random. These are not known. That should be equal to the level in the next month, plus the amount that we use, the water we use for power generation. And there is also spillage, ST. ST is the amount of water that, that is not used for power generation, okay? And of course, we have bounds on these parameters. So it's a very well-defined problem. And so this is what we use in the context of expected conditional risk measures using the different risk measures. For the numbers I'm going to show you, we actually used expected excess. This is a classical problem that has been done for the Brazilian network. We have several thermal plants. You can say it's a huge number, it's about 95. They have different regions in Brazil. Each region has different things, but this is kind of a simplified network. And so we looked at all these different regions. Just to give you an idea, 84 stages. This is like 7 months. 25 different observations each month for the different inflows. And so it's a huge number of scenarios. So the only way to solve this is to use some type of sampling, and SDDP allows you to do that. And we experimented with different lambda values here, risk levels. Larger lambda means, you are risk averse, and also you have to set your targets. The way the targets are set is based on the application. In this case, they used the 90% quantile of the risk neutral. So they solved the risk neutral solution and then used the 90% quantile. Anything above that, they considered it to be too risky, okay? And this graph just shows the algorithm iterations, the upper bound, lower bound, to just illustrate that it actually converges. Here is what I wanted to show you, just a quick one, and I have one more slide, then I'll stop talking. So on the vertical axis, we have the cost, okay? So this is the cost per megawatt. We are trying to minimize the cost. Lambda equals 0 means risk neutral. So for the dark line here, the black line is risk neutral. So this is lambda equals 0. And then we trace these lambdas all the way to over 100. In this case, I'm just showing 0.5, 5, 10, and 1, just to kind of illustrate what's happening. So now, so when we solve, we get an optimal policy. And then we sample, we get 7,500 samples. And then we apply our optimal policy to those samples. And so we can construct quantiles, okay? So we talk about 50% quantile. So it's more like the average. So if you think your future is going to be average, then we can see that using the risk neutral is the best thing to do. So the risk neutral solution it gives you the minimal cost, okay? Risk averse is going to cost you, okay, because there is no extreme scenario. So it's going to cost you, but later on you may do okay in the in the future, okay. But overall, I think risk neutral shows is the way to do it. We go to the 90% quantile. So now we are trying to look at bad scenarios. We start seeing that taking risk into account starts to pay off. Risk neutral starts out well, but then it does poorly in the future, okay? We keep increasing the bad scenarios. We see 99% quantile. If you're really risk averse, you can see that you will do well if you have a bad future. Again, you can't tell a priori how the future is going to look like. Just like with COVID-19, who could predict that this could happen? But if you are risk averse, then you can actually do this kind of analysis and then decide which of these lambdas you want to use for your decision making. So these results actually illustrate clearly that taking risk into account in the multi-stage setting can pay off when you have bad scenarios happening rather than using risk neutral. Risk neutral is good when things are good, when things are nice, okay, on average, then it's good to just use the risk neutral approach. This one just shows for the Southeast, what's happening with the reservoir levels in terms of the power generation. On average, if you have the 50% quantile, this is the average case. And now we're looking at the levels. So we have 50% quantile, 10%, 5%, 1%. This is a nice case. You can see that all these models, they're actually keeping some water in the reservoir. So the future is coming. So they keep more water in the beginning and use more later. Okay, that's what this shows. Again, as it becomes more, where it becomes worse when you get here, you can see that, in many cases, the risk neutral basically ends up with no water in the reservoir, which means you use more of the thermal. And that's why it costs more when scenarios are bad for the risk neutral case. And it's better to use, risk averse like lambda equals 100 is, for this case, what we found to be, something that was acceptable for the Brazilian guys, okay? So just to summarize, we have been studying risk-averse models for multi-state stochastic programs based on a new risk measure called the expected conditional risk measure, which is time consistent, and we have derived, Bellman equations for this, and therefore we can actually use classical methods like SDDP. We have done lots of experiments, not only for hydrothermal, but also for portfolio optimization. For the sake of time, I didn't show you those results. But the results show that ECRMs can provide, superior solutions to the risk neutral case when you have bad outcomes for the future. So some of the things that we are looking at now is developing other risk measures we can use in ECRMs, but we are deriving other convex risk measures. The other thing we are doing is trying to compare how the policies look like for the ECRMs versus other frameworks like nested SIVA and also multi-stage distributionally robust models. So this is some of the things that we are doing. With that, I will stop and take any questions or comments.
Thank you very much, Professor Ntaimo.